See you all, thanks for coming in. Our plan today, we're going to work through this 2016 Maths Studies exam together. So you might remember 2017 the course changed, and so some things were brought in, other things were pushed out, and it moved from in 2019 it moved from a 3-hour to a 2-hour exam. So what I've done is I've taken the old Maths Studies exam and I've pulled all the stuff out of it that's not relevant, and I've added a couple of questions in as well. So it's all stuff that's relevant to the course. And so it's just sort of adapted. It's stuff none of you have seen before, so we're going to make our way through it. Although you may have seen some of it in the revision guides. I'll be interested to hear if you haven't. So that's what we're going to do today. And then on Friday I've got like my spec and methods lessons back to back. So I thought what I'd do is offer another trial exam. So it's not me coming up going through it, but I'll make another exam like this one for you to come in and sit under exam conditions, okay? Voluntary, but could be a good idea familiarising yourself with that exam situation, maybe noticing last minute things you need to do. If you want, I'll even mark them for you, otherwise I'll provide some solutions, so sounds good. Excellent, let's get straight into it. So yeah, feel free to charge ahead. We'll just go through it at a steady pace, I think. There's a bit over 100 marks, so this is going to be a little bit longer, not much, I think it's about 110 marks, but this will be a little bit longer than the exam. So I anticipate it taking us about an hour and a half, 2 hours. Okay, so we've got some derivatives to do. So we've got the first function here, 10 times 2x, take the square root of x to the power of 4. So this is going to be the chain rule. We have a function of x to the power of n. So come grab an exam up here, guys, and then grab a seat. Function of x to the power of n. So we'll get straight into the chain rule. Just remember that's x to the half, isn't it? Okay, so here's the chain rule. 10 n f of x to the power of n take 1. N f of x n take 1, and then that's multiplied by f dash of x, the derivative of the inside component, which is that. Okay, so remember we've spoken as we're going through these about some marks in the exam are easy to get, some are hard. This is an example of 2 marks that are easy to get, so you've got to make sure you get it. Alright, so that's part A. Part B, we have x to the 3 times ln of x squared plus 1. X to the 3 times ln of x squared plus 1. This is a product rule. No need to simplify, so just show clearly the u, v, u dash, v dash components and smash it together. Very good. All right, next we've got 3 normally distributed random variables, A, B, and C, all have the same mean, 10.2 grams, but they have different standard deviations. A has a mean of 10.2 and a standard deviation of 0.7. What proportion of A is heavier than 11.5? So let's understand it. Here's the distribution of A, has a mean of 10.2, standard deviation of 0.7, and we're saying what proportion is heavier than 11.5. That's what we want to calculate. This is a normal distribution calculation, NCD. Lower boundary is 11.5, upper boundary infinity. We're told the standard deviation is 0.7, and the mean is 10.2. So let's calculate that. So I haven't calculated any of these. I did write solutions, but I've lost them. So I'm just going off what I remember and knowing how to do it. Infinity, 0.7 and 10.2. All right, I've got 0.0316. 164, so 4 rounds down. All right, given that the probability of the distribution of A being less than some number A is equal to 0.1, find the value of A. Okay, so here's the distribution of A, right? And we've said the probability of this distribution being less than this number is 0.1. Find the value of A. All right. So this is an inverse normal calculation. We've got the area, we've got the tail is on the left, we've got the mean, and we've got the standard deviation. So inverse normal, let's list all those components that we need. Distribution or tail is left, area is 0.1. Standard deviation 0.7, mean 10.2. And so we've got A is 9.30. So what this means is the probability of the distribution being less than 9.3 grams is 0.1. All right, so that's part 1. Part 2. Question B. The distribution of B has a mean of 10.2 grams. And it is known that the proportion of B that is heavier than 11.5 grams is 0.11. Use this information to sketch the distribution of B. So here I've provided a bit of a sketch of the distribution of A based on what we know. Here let's draw the distribution of B. So it's going to look like that, has a mean of 10.2. We don't know its standard deviation, but we do know that 0.11 is larger than 11.5, right? So if that's 11.5, this has an area of 0.11. So I think you probably get 1 mark for doing that. I haven't seen the marking scheme for this exam. I think they're looking for one other piece of information, which is if we know that area is 0.11, then we also know what this number is here, such that the area is 0.11, because it has to be symmetric about the mean. How much do you have to go up from 10.2 to 11.5? You're going up by 1.3. So therefore, to get to this point, you have to go down by 1.3. So that's going to be 9.2, 8.9. So I think that's where you get the second mark there. So distribution of B. All right, move on. Calculate the standard deviation of B and give your answer correct to 2 decimal places. All right. So let's list the information that we know about B. So we know for B that the probability of B being larger than 11.5 is 0.11. Okay, we've got the distribution of that sketched over there, and we know the mean of it is 10.2. So what we're going to do is we're going to compare this distribution with the z distribution, right? The z distribution has a mean of 0, standard deviation of 1, and we're saying, what is this as a z-score? What's the z-score of this one? 11.5. And then we're going to use the z-score to calculate the standard deviation. All right, so if that area is 0.11, what's the z-score that corresponds with it? So for the first part of this question, we need to go inverse normal calculation. We're doing our tail to the right. The area is 0.11. Standard deviation of a z distribution is 1 and the mean is 0. That's going to give us the z-score that corresponds with 11.5 on the B distribution. So 0.11. Alright, we have a z-score. The z-score is 1.2265, 1.227. We'll leave it to 4 figures for now because that's not our final answer. Now you might be a bit confused as to why I've had to find the z-score. We're asked to find the standard deviation, right? And remember, this is what the z-score is. X take mean divided by sigma. We've got the result. X is 11.5. Okay, that's corresponding with this z-score. We've got the mean is 10.2, and we're asked to find the standard deviation, right? That can be rearranged. You can rearrange it before you sub in or after, doesn't matter. Swapping the mean, the z-score, and the standard deviation. So, we had X was 11.5, the mean was 10.2, and our z-score was 1.227. We'll plug all that in to get the standard deviation for B. Alright, and we've got the standard deviation is 1.059. Go to three figures because it's our final answer. 1.06. Alright, so that's pretty tricky. 3 marks there. This we do in exercise 8F.2. So if it's a skill you need to reiterate, scribble that down, that's where we're doing that one. Alright. Excellent, let's move on. We've got C. Now we've got the distribution C. C also has a mean of 10.2, and it is known that the proportion of C that is heavier than 11.5 is 0.087. So here's C, here's its mean, here's 11.5, and we have an area of 0.087. Okay. Is the standard deviation of C less than or greater than the standard deviation of B? Give a reason for your answer, but do not calculate the standard deviation of C. Now, even if you haven't figured out what the standard deviation of B is, you can still answer this question. And the way we're going to do that is we're going to compare this area with this area. Okay? Both of them have the same mean, alright? But this one is more spread out, and it's more spread out because it has larger area further along. It has a larger area. And so for that reason, this one has a larger standard deviation. It has to, because the distribution is more spread out. And so therefore our answer is the standard deviation of C is less than, and we need to describe why. So let's see if we can come up with a good way of describing that. So sigma C less than sigma B. Okay, that could be one way to write it mathematically. Why? Why is this the case? So let's see what I can think. The area of C more spread out. That would be a very appropriate way to justify it. So the area of B is larger than 11. The area of B larger than 11.5 is larger than the area of C, which is greater than 11.5. Therefore, B is more spread out. Therefore, it has a higher standard deviation. All right. Any questions so far? Very good. Very good. Okay. We've got, consider the function f of x equals x on x take 4, and we're restricting the domain here. We've got x is larger than or equal to 0, and x does not equal 4. Alright, so they're the restrictions on the domain. Okay, part A. For what values of x is f of x decreasing? So you just look at the function, it's decreasing if, as you walk along it, you're walking downhill. And remember, we're always talking about moving from left to right. So you can see we're decreasing from 0 to 4. like we're decreasing for all values, right? But it doesn't exist at 4. So we're decreasing, that's the first interval. We're going to describe it like that because it doesn't exist at 4. All right, and for x is larger than 4. All right, it's also decreasing for x is larger than 4. Okay, find the average rate of change from x is 5 to x is 7. All right, so let's refresh some language for you. I'm just going to provide a very rough sketch of it. Average rate of change means the slope over that interval, and we call that line a chord. Okay, that's the technical language for it. That's a chord. It's the slope of the line between x is 5 and x is 7. All right, so the slope, right? The slope, we need y2 take y1 on x2 take x1. We need 2 coordinates. And we've got the first coordinate, x is 5. What's the y coordinate? Well, the y value is going to be 5 on top of 5 take 4. 5 on top of 1, 5. Okay, so the first coordinate is 5, 5. You can confirm that from your graph. You can see that there. 7's a little bit more tricky because we have, when x is 7, y is going to be 7 on top of 7 take 4. That's 7 on 3, right? And so what's that? That's 2.3 recurring. Okay, so let's sub them in. Now remember, it doesn't matter really which one's y2, which one's y1, as long as x1, y1, x2, y2, as long as the subscript belongs to the same coordinate. So y2 is 5. Take y1 on x2, take x1. y2, take y1 on x2, take x1. All right, let's evaluate that. So we've got 5 take 7, we've got minus 2 at the bottom. Now 5 take 7, like there's a, just chuck this in your calculator, right? You know, we're going to solve it, but here we go. We need 5 to have the same denominator. So that's going to be 15 on 3, take 7 on 3. Okay, now 15 on 3 is, well, we've got the same denominator, so now we can form it. 15 take 7 is going to be 8 on 3 on minus 2, minus 8 on 6, minus 4 on 3. All right, so we put it in the calculator, minus 1.33. We can like look for confirmation with these things, all right? You've evaluated this and we've got a negative number. Of course it's negative, it's going down. As we walk along, we expect the slope to be negative over that interval. So that's the average rate of change, the ARUC. On the graph, draw a representation of it. So draw that chord there on your graph. Okay, and then the first principles. Using first principles, find f dash of 6. Okay, so first principles, you're welcome to charge ahead and have a bit of a go at this one yourself. All right, I'm just going to work through it a bit up here. So let's just make the statement first. That's our first mark. X plus h on top of x plus h take 4. So f of x plus h, take away f of x on top of h. That's the first step, isn't it? Make the statement. This is what we need to process. If you want, like, you may have seen this in the revision guide as well, right? What we're doing here is I'm processing it for the slope function, and then I'm going to put 6 into it, all right? You can even put 6 in straight away. Like if you want to know f dash of 6, you can just put 6 in straight away and keep processing it like that as well. But if you're not familiar with that, let's not confuse it. Okay, so we're just going to do f dash of x. All right, so if we want to process this right, it's always the same. The first thing we need to do, bring them together. We need to mash them together somehow. At the moment we can't because they don't have the same denominator. So we need to make them have the same denominator. So what we're going to do is we're going to cross multiply the denominators. We're going to multiply this one by that denominator. X plus h take 4 on x plus h take 4. And we're going to multiply this one by that denominator. X take 4 on x take 4. Now brackets are useful here just so you can, or a multicolour so you can see their separate components. So let me show you what that's doing, right? Just in terms of numbers. This is effectively what we've got. We've got 5 on 3, take 2 on 7. We've effectively got some operation like this. They have different denominators. So if we multiply this one by 7 on 7, all right, we're multiplying it by 1, so we're not changing its value. It's a legit operation. Multiply this one by 3 on 3. All right, and then let's process it a bit. This one becomes, what, 35 on top of 3 7s, 21. This one becomes 6 on top of 21. And then because they have the same denominator, you can bring them together, right? 35 take 6 on top of 21, and you can process it. That's what we're doing, okay, when we cross multiply. So let's go to the next step. Don't forget the brackets. Now with these ones, you should never have to, expand the bottom. And I might point out one thing as well. This is the function that we're finding the derivative of. Okay. So if you were to do this using the quotient rule, right? You've got u on top of v. So you know when you process it, right? The bottom is going to be x plus 4 squared. That's what the denominator has to be. And we can confirm that over here. If we've got x plus h take 4 times x take 4, when you sub in the h, that's going to disappear. You have x take 4 squared, right? And so that's showing us we're on the right path. It's showing us that's what the denominator is. All right, I'm rambling. The h can come up here. We've got, on top of 1, AD on BC. And what we're going to do in the next step is we have to expand the top. It's always expand the top, collect like terms. So let's do that. We'll first expand, then we'll collect. Okay, collect. H will cancel. Now we'll apply the limit as well. So when we apply the limit, we don't need to write that step. Minus 4 on top of x take 4 squared. That's the derivative function. Okay, that's f dash of x, but remember we're not finished. We get our fifth mark by substituting in 6. Now, this question here is the type of question that I'm very confident that they won't ask this kind of thing. And I'll point out a bit more at the end as to why. But I've intentionally left it in here because I think it is a useful skill for us to be able to assess something and extract the necessary information from it. So let's read it. Consider the function. We've got x to the 3 plus ax squared plus bx plus c. The graph is shown below. The tangent to the graph at the point 2 minus 6 is also shown. So we've got a tangent there. And we've got the equation of the tangent. This tangent intersects the graph at its y-intercept. Write down an expression for f dash of x. Okay, so we've got f of x is x to the 3 plus ax squared plus bx plus c. We're just going to differentiate that. We treat a, b and c as numbers. 3x squared plus 2ax plus b. That's the derivative function. Okay. Hence, show that minus 4a plus b equals minus 17. Hence, show that. Hence, okay, it means using what you just did, using the derivative function. We have to use the derivative function somehow. We are told some things in here, but it's very sort of hidden. We need to extract it out. We've got the equation of the tangent. And what does the tangent tell me? Okay, it's y is mx plus c. N, what is n? N is the slope. We know when x is minus 2, the slope is minus 5. Okay, so that's pretty difficult to pull that out. That's the trick they're looking for. When x is minus 2, f dash of x is minus 5. If we plug that in, we should get the answer they're looking for. So, f dash of minus 2 equals minus 5, which is going to be let's process it. 3 times 4, 12. Take 12 from both sides. Alright, so that's how we arrive at that one. We know when x is minus 2, f dash of x is minus 5. Alright, using the information given, determine 2 additional linear equations that involve the unknown coefficients of f of x. So this is one linear equation, right, between a and b. We need to see what other information can we extract about this graph. So the first thing is we're given the coordinates of the tangent. We're given minus 2 and 6. Alright, so that means when you put x is minus 2 into this equation, f of x equals 6. So there's one. Let's do that one. Alright, so that's the original function, right? We're putting it in the original function. Here, that was the derivative. So we've got 6 equals okay, so there's one equation. Alright, so just from the point on the graph, we know minus 2, 6 exists on the graph, so it has to satisfy the equation of the function. Alright, and then the other one is the equation of the tangent is 5x take 4. And the tangent intersects the graph at its y-intercept. So look at this point here. That's fascinating because our tangent here has a y-intercept of minus 4, and the function also has a y-intercept of minus 4. So that means when x is 0, y is minus 4. So you can make that statement if you want. When x is 0, y is minus 4. If you sub 0 in, you're going to get c. So the value of c is minus 4. Okay, and then you're finding the unknowns, right? So that's part B. And then you're on to part C where it says to find the values of A, B, and C. Now, the reason I don't think they'd ask this question in particular is because simultaneous equations, so that part there, 3 systems of simultaneous equations are no longer part of the studies course. But nonetheless, I think we can solve this one reasonably easily. We've got c is minus 4, okay? And if I put that in there, let's put that one into here. We can solve it by substitution. we've got 14 equals 4a take 2b take 4. We can move the minus 4 over. So we have 18 equals 4a take 2b. And look at these two linear equations. Okay, we have done that. We've done systems of two linear equations. So minus 4a plus b equals minus 17. And 4a take 2b equals 18. You can put it in your calculator to solve them. You can solve them by adding them together. Yeah, we can go ahead and find a solution. I'll just go c is minus 4. One of them is positive 4 and one of them is 1. Can't remember which way it is. Yeah. All right, let's move along. Question 6. All right, so yeah, I do think that is a good question because it does allow us to reflect on where functions meet, how we can use the information we're given and so forth. Okay, here we have a function, e to the x on top of 2 take x squared, and it says, show that f dash of x is this. Now this is the only circumstance where you're required to simplify, right? Where you are required to simplify it to a. So here you need to use the quotient rule. We have one function divided by another function. All right, so I'm going to let you guys do that really quick. I think you can go get my water bottle. U dash v, take u v dash, so that's going to make that plus on top of v squared. All right, and it's almost the same, but they do want us to factorise the e to the x at the top, right? E to the x is common to both of these terms, so we're going to pull that right out the big front. And we're going to be left with 2 take x squared plus 2x. And then on top of 2 take x squared. So now we've got the same way. They've swapped those terms around. That's fine. Okay, find the equation of tangent at the point where x is minus 1, sorry. Give your answer in terms of exact values. So we're finding the exact equation of the tangent. For a tangent, we need two things. We need the point of contact and we need the slope. All right, so point of contact and slope, and then bring them together. Now, the point of contact is x is minus 1. We need the y value. Okay, occasionally you're given the y value, you need to find the x value. Here we're given the x value, and we want to know what's the corresponding y value. We substitute that in to the original equation. All right, it's going to be, I'm going to process it a bit so we can simplify it. It's e to the minus 1 on top of 2 take the minus 1 squared. So that's, yeah, we'll leave it like this, e to the minus 1 on top of 2 take 1. It's e to the minus 1. You can leave it like that, or you can express it like this, 1 on top of e. Either of those is perfectly suitable. But be aware of the relationship between them. Okay, and then for the slope, so let's use the slope function. We're going to put minus 1 into the slope function here. process this. Hopefully don't get copyright on the video. So we've got 2, and I'm looking at this, minus 2, so they're just cancelling, okay, there's going to be stuff that cancels. We've got minus, and then this is minus 1 squared, so that becomes positive 1, so we've got minus 1 at the top, and then at the bottom we're going to have 2, now hang on, that squared at the bottom there's 2 squares, don't let me forget, there's one there and then there's one there. So it's 2 take positive 1, so it's 1 squared, we've got 1 at the bottom as well. So there's a bit going on there, use your calculator to help you if you're unsure, but we've got minus 1 at the top, positive 1 at the bottom, and so the slope is actually almost the same, except it's negative. The slope is almost the same, except it's negative. So I'm going to put the slope like this, minus 1 on top of here. Okay, there we are. We've got everything we need to find the equation of the tangent. Point of contact and the slope, let's bring them together. We've got y equals mx plus c, n is minus 1 on e. And we know when x is minus 1, y is 1 on e, so that's the point we're going to substitute in. One on e equals 1 on e plus c. C has to be 0. So therefore the tangent is minus 1 on ex. That's our final answer. Alright, question 7. Find the integral of x squared plus kx take 24. So just set the value of x squared plus kx take 24. We'll have x to the 3 on 3 plus kx squared on 2 take 24x plus c. 2 marks. Oh, nice. Very nice, easy 2 marks. Consider the function shown below, the graph of it's here. The region, the shaded region bounded by y equals f of x, the x-axis and the y-axis, and the line x equals 3 has an area of 72 square units. Using the answer to part A, find the value of k. Alright, so what does this mean? The integral from x is 0 to 3. Alright, the area under the curve of this function equals 72. I'm missing one thing. Squared? No. It's below the x-axis. This area is below.
Does it have a negative?
Correct. Yeah, there's a negative here because it's below the x-axis. And so you can put that there if you want, or you can just shove it straight over here. We're trying to solve for k, aren't we? So we can shove it over the other side. All right, and let's just go ahead and process that. We're going to have, we know what it integrates to, right? It integrates to x to the 3 on 3 plus kx squared on 2. 24x. We don't have c because now it's a definite integral. We have the boundary. And when you put 0 into this one, that's all going to 0. So we don't need to consider that component of it. So we'll put 3 in. So I'll show you. And from here, feel free to use your calculator. We can just keep processing it. We've got 27 on 3 is 9. We've got 4.5k. And we've got 24 times 3, 72 as well. Alright, so we've got negative 72 on both sides. We can get rid of those. So we've got 4.5k equals 9, negative 9. So k is negative 9 on 4.5, negative 2. Yep. All right. Okay, next we've got a question. We've got sign diagrams of f of x, f dash of x, and f dash dash of x. Now they like to ask these questions. They're pretty common, and they're pretty hard as well. They can be pretty hard. Okay, so we've got this, let's read it. We've got the sign diagrams below relate a function to its first derivative and second derivative. Okay, all shown there. Part A, for what values of x is f of x increasing? Okay, f of x is increasing if it has positive slope. So we're looking at the sign diagram of the first derivative, the slope function, right? When is it positive? It's positive for values less than or equal to minus 2. When we're talking about intervals, we always include the point. Okay, then we've got a table to fill in. F of x has two stationary points, A and B. Determine the x coordinates and classify. Alright, so I'm going to provide a rough sketch of it up here. So A and B. Alright, so turning points occur. Turning points, that's when it changes from increasing to decreasing, or decreasing to increasing, or it's increasing and it goes horizontal and it keeps increasing. They're the stationary points. And they occur when the first derivative is 0. So the first derivative is 0, we're looking at the equation of the first derivative. And the first one is minus 2. X is minus 2. Right? That's where we have a stationary point. And what the slope tells us is it's increasing, has 0 slope, and then decreasing. So what's that? Increasing, decreasing, that's a local max. Alright, so we have these ones written down. We're going to have the sign diagrams on our cheat sheets, but yeah, we'll go that too. And then we look for the second one. Where does the first derivative equal 0 again? At positive 1. And is decreasing, goes horizontal, and then keeps decreasing. Okay? That's what we call stationary inflection. Now, in the exam, I wouldn't write POI, I would write point of inflection. Okay, then we have to sketch a graph of this function. So we've got to use all the information we're presented with to try and come up with a graph of it. So the first thing we want to use is the sign diagram of the function, okay, because that tells us when it's above and when it's below the x-axis. So we can see it's got a root at minus 3 and a root at positive 2, okay? It's below, and then over this section it's above. We also know that we have a local max. In fact, what we might do, I might just go through and list all of the things we know from each, and then explain, then we'll draw a graph from it. Okay, so we know it's above the x-axis over this region, and below here, and below here. All right, so it's crossing here somewhere, and crossing here somewhere. Okay, so that's the first thing we know. That's from the sign diagram of the function. Let's look at the sign diagram of the derivative function. That's told us these two things. We have a local max at x is minus 2. All right, so that means it's doing something like there's a maximum point there. Here's minus 3, here's minus 2. So there's going to be some maximum. It's going up and then it's going to come back down. And then the other thing we know is there's stationary inflection. That's what we did here, stationary inflection at x is 1. And from the sign diagram, what it tells us is it says it's got negative slope, it goes horizontal, and then it has negative slope again. So that's occurring at x is 1. Let's put that there somewhere. Negative slope, all right, goes horizontal, and then has negative slope again. All right, so we're starting to bring those things together. Okay. And then we've got the sign diagram of the second derivative. So you could, if I imagine, if you were just to connect those up, you'd probably get the full 3 marks. But let's really provide a thorough insight into this graph to say, what's the second derivative telling us? Two things. Firstly, we're aware of this point of inflection already. Okay, so remember the second derivative, when its sign diagram is 0, they're the points of inflection provided it changes sign. And we can see it goes negative, positive, negative, so it's changing sign. The other one is we've got another point of inflection at -1. So at -1 here, we have some other point of inflection. And by you connecting them, you would inevitably show that. But we're going to exaggerate it a bit. We're going to try and exaggerate it a bit. Okay, so let's do that. All right, so you can see concave down, and then here it's changing to concave up. That's how I'm going to exaggerate it. And then back to concave down. All right, look at that. Point of inflection there. Point of inflection there. Concave up, concave down, and then here it's concave down. And that's confirmed also by the sign diagram of the second derivative. Okay, it's negative for values less than -1, concave down, and then it's positive because it's concave up over that interval from -1 to 1, and then concave down. So there we go. All right, let's move on to the next one. So yeah, there's a whole booklet on those questions, and I do recommend, going over them, re-familiarising yourself with them. All right, we've got, when a 6-sided die is rolled, its outcome is the value shown on each upmost face. A fair die is one which the probability of each outcome is equal. If this die is rolled 80 times, what is the probability of obtaining an outcome of 6 exactly 20 times? Okay, so this is a BPD. We either get 6 or we don't get a 6. Okay, they're the events, all right? You get a 6 or you don't get a 6. And we're saying, what's the probability of our variable being equal to 20 exactly? We're having 20 successes out of 80 trials. All right, so 2 ways to do this, right? BPD, 20 successes, 80 trials, and the probability of getting a 6 is 1 in 6. All right, let's relate that to the binomial distribution formula. All right, remember that one? Okay, binomial distribution formula. Both of those are going to generate the same answer for you. Has anyone calculated it?
0.1.
0.1?
0.017.
0.017, thank you. All right. How about obtaining an outcome of 6 24 times or fewer? So that if we think of how many times we get a 6, right? They're saying 24 or less. Okay, so now they're talking about multiple outcomes. So that's going to be a BCD. All right, we're talking about multiple outcomes, and our lower boundary is 0, because we could have no 6s, and our upper boundary 24, because we're saying up to and including 24 or fewer. And out of 80 trials, probability of success 1 in 6. So that's the one we're going to evaluate there. Anyone done it? All right, 0.999. Okay, and then part 3. How about obtaining a 6 between 16 and 24 times inclusive? (16 and 24 inclusive). So just same calculation, just changing the lower boundary to 16. And we've got 25%. Very good. So a couple of marks there, reasonably okay to get. All right, now we've got a weighted die. A weighted die is one to which weight has been added in order to increase the probability of one of its outcomes. The probabilities associated with a weighted 6-sided die are shown below. What is the probability of rolling this die 80 times? and obtaining an outcome of 6 exactly 20 times. So almost the same calculation, except things have changed, right? BPD, we want 20 successes out of 80 trial, but now the probability of success is 0.25. All right. 20, 80.25. We've got 10%. A die that might be fair or might be weighted. Ooh, we don't know, we're testing it. This die is rolled 80 times and an outcome of 6 is obtained 20 times. Calculate the 95% confidence interval for the proportion of times that this die, when rolled, has an outcome of 6. All right, so in stat mode, we're doing a confidence interval. So interval Z, and it's for a proportion. We don't have a mean, we don't have a standard deviation. We've just got an event happening out of n trials. So our confidence level, 95. Our 20 successes out of 80. So that's the information we're putting in. And we've got 0.155. So 0.345. All right. Is this confidence interval consistent with a fair die? Well, if it's fair, what's the probability of a 6? 1 out of 6, which is 0.16 recurring, right? Which exists in this confidence interval. So the die could still be fair. Is it consistent with a fair die? Yes, as the outcome for a fair die, 1 on 6, lies in the confidence interval. All right, again, I'm doing this shorthand up here, but in the exam, I wouldn't assume that they know what you mean when you say CI or POI or those kinds of things. POC, write them out. Okay, part 3. Hence, what can you conclude about whether or not the die being tested is weighted? All right, well, it's inconclusive. We don't have enough evidence to say that it's not fair because the 1 on 6 lies in the confidence interval. So that's what we should say. The test is inconclusive. Okay. All right, now we're performing a pretty similar experiment. An experiment is designed in which the die being tested is rolled a number of times. Determine the minimum number of rolls, 1/4 of which have an outcome of 6, for which the confidence interval obtained would not be consistent with a fair die. I'll let you process that for a minute. Experiment is designed in which the die being tested is rolled a number of times. Determine the minimum number of rolls, 1/4 of which have an outcome of 6, for which the confidence interval would not be consistent with a fair die. Okay, so for the confidence interval, all right, here's our confidence interval. We've got the lower to the upper. For it to not be consistent with a fair die, this has to be bigger than 0.1666 recurring, right? The lower boundary of this confidence interval has to be larger than 1 on 6. And if the lower boundary is larger than 1 on 6, then we've got good evidence to suppose it's not fair. So, 2 ways you can go about it. There's a trial and error process, or you can write an equation for it in the calculator. I'm going to show both. So the first way is with the equation, right?
Where it began.
So for a 95% confidence interval,
I can't begin
we have p hat, take 1.96 times times what? Square root of PQ on N. Okay? That's the lower boundary of the confidence interval for a proportion, right? And that has to be larger than 1 on 6. Alright? Now, in this circumstance, what is P? Alright? P is a quarter. Why is P a quarter? Why is P a quarter? Because it says it doesn't matter how many trials we do, but a quarter of the trials are 6s. Alright, so that means our observed value of successes is a quarter. So if you sub a quarter in there, 1.96, so I'm simplifying a bit now, we have 0.25 times 0.75 on top of N. What are we solving for? We're solving for N, because we want to know how many times we do this experiment, such that it's larger than 1 for 6. Okay, so now, alright, I mean, if you want, you could go ahead and solve that equation, alright, you can take 0.25 from both sides and multiply by 1 point. Sounds like a long way to do it. You can put it in equation solver, okay, you could make it equal, and then round N up to guarantee it's true. Okay, so that's how we can do it using the equation process. That's a little bit more complex, I think, than the trial and error. For the trial and error, what we're doing is we're going to the confidence interval. All right, and maybe you guys will be pretty happy with this answer. It's a fair bit easier. We're going to go to confidence interval. Our level is 95%. All right, and we have X and we have N. Now we need to keep changing X and N until we get a lower boundary larger than 1 on 6. So what did we have? We had 80 and 20, okay? And we saw that with 80 and 20, the lower boundary was, we wrote it over here, 0.155. So then you might go, all right, what's the next number we could use? So if we went 21, this has to be 84. All right, because that 21 is a quarter of 84. You check that, all right, not going to be large enough. Then you go say, oh, I'm just going to go a bit higher. Let's do 25 and 100. All right, I haven't written it down, so I'm going to process this one. All right, 25 and 100 is a quarter. So we do that. We're getting close. Look at that. We've got 0.165, but it's not high enough. We need to go a bit higher. That's 0.165. So they're the next whole integer value. Let's go, what about with 26 and 104? 26 is a quarter of 104. 26, 104, cracked it. Okay, that's 0.1667. All right, so if we were to perform the experiment on the die, and we saw that it got 26 successes out of 104 trials, that would be enough. That would be a large enough confidence interval to say the die is weighted, because it's above what it should be. The lower boundary is above what it should be. So they're a tricky 3 marks to get, right? They're a tricky 3. We'll move along. Okay, question 12. Sketch a graph. So consider the function where x does not equal -1. Sketch the graph clearly showing axes, intercepts, and the vertical asymptote. I'm going to sketch it up here because we might need to refer to it. We'll see. So just make sure we've got a vertical asymptote at x is -1. So we can see that from looking at it, right? Because x plus 1 is the denominator. Can't exist when the denominator is 0. So we know there's a vertical asymptote there. There's Moss here. X to the 3 on x plus 1. Alright, so that's what the function's sort of looking like. There it is there. Okay, so yeah, where's the vertical asymptote? Here, it's the equation x equals -1. that's where the asymptote is. Indicate that with the dotted line. All right, I'll move along. We all know how to graph. Make sure you get the 3 marks for graphing. All right, so trace along it, make sure it's in the right location and so forth. Graphing is an easy 3 marks to get, right? The graph has 2 stationary points. One of these stationary points is 0, 0. Find the x coordinate of the other stationary point. So just by looking at it, stationary points, their minimum, maximums, and stationary points of inflection. There it is there, the x value, minus 1.5. Yeah, minus 1.5. Leave it like that for me. Okay, now consider the function x to the n on top of x plus 1, where n is a positive integer, and n is greater than 2. For all possible values of n, the g of x has 2 stationary points. One of them is always at the origin, and the other stationary point is at A. Complete the following table in the form A on B, where A and B are integers. Okay, so we've got the x coordinate of point A. Point A is what? The other stationary point on the graph. Now here, this is the stationary point when n is 3. When n is 3, we have minus 1.5, but it wants us to express it as a fraction. Minus 1.5, what's that as a fraction? Minus 3 on top of 2. Okay? All right, next one, so we just have to change the power. All right, so we're going to go, what about when x is 4? All right, and say what's the stationary point now? When x is 4, now look carefully, the stationary point's gone down here, minus 1.3 recurring. What's that as a fraction? If you're not sure, fiddle around on your calculator, but 0.333 means it's a third, and we've got 1 plus a third, 4 on 3. So we're going to go negative 4 on 3 there for that one. And then the last one, and maybe you're starting to see a pattern, minus 2 on 1, minus 3 on 2, minus 4 on 3. Change this to a 5. And so this function is pretty cool. It's going to oscillate back and forth above and below the x-axis. Minus 1.25. All right, so 0.25 is a quarter. So we've got 1 plus a quarter, we've got 5 quarters. All right, minus 5 on 4. And so here's 4, 5. All right, so now it says make a conjecture. On the basis of your answers, make a conjecture about the x coordinate of point A for the function. The x coordinate of point A. So you can write it like this, the x coordinate of point A, and its relationship to n. How is it related to n? Okay, so it seems like n is the top number, and the bottom number is n take 1. All right, it's 1 less, and there's a negative out front, right? Yeah, now that could be written like that. Another way it could be written, and it would be perfectly fine to do so, is like that, where the negative distributes into the bottom, so then you don't have any alpha. Either of those, perfectly acceptable. Prove or disprove your conjecture. Okay, so we've got the function g of x, x to the n on top of x plus 1. And we're finding the x coordinate of the stationary point. Okay, stationary points occur when the first derivative is 0. So we need the first derivative. All right, for that we're going to have to use the quotient rule. We've got u is x to the n, u dash n x to the n take 1. On top of and bottom of x plus minus 4. So that's g dash of x. Now we should communicate this a bit, be nice and clear about it, rather than just performing the maths, we should communicate what we're doing. And so what we're going to do is stationary points occur when g dash of x equals 0. Okay, so therefore this equals 0. And if we have a function equal to 0, then that occurs when the numerator equals 0. We can completely disregard the numerator, because that's when asymptotes occur, but for the function to be 0, the numerator has to be 0. So therefore, we're interested in the top component of it. And we're solving for x. We want x by itself. Okay, so whenever we've got multiple x's, we definitely want to factorize. We want to factorize whenever we can. So we are going to factorize x to the n. All right, and you might say x to the n is here, and it is here, but it's not here very clearly. So I'm going to show you how it is there by just pulling it out the front. So if we pull x to the n out the front, then what we're going to have here is n times x to the minus 1. All right, let's just focus on this part. X to the n times nx to the minus 1. They have the same base, so you would add those powers together, and the n's just hanging out the front. Okay, so that's legit. That's a cool operation. We've got x plus 1 here, and then we have to take 1 here equals 0. All right, let's apply the null factor law. X to the n equals 0. That's the stationary point they've already told us about. That occurs when x is 0. Okay, that's the stationary point 0, 0. So that's fine. So then we're interested in this component. Now I'm going to write that like this. N 1 on x. X to the minus 1 is 1 on x times x plus 1. Take 1. And I'm also going to distribute the 1 on x. So we're going to have n times 1 plus 1 on x. We want x by itself. Okay, we're trying to get x by itself. So let's move that 1 over the other side. We'll divide both sides by n. Now I might be going about this a long way. We'll subtract 1 from both sides. You can see we're breaking it down. And then we will, let's collect them and then we'll reciprocal both sides. And now reciprocal. Alright, so I probably went about it a roundabout way there. The point is, you keep processing it, you keep cracking it, you keep breaking it down. Q to the D. Okay, so we got 3 questions left. Very good. Alright, this one here, just differentiate. Now, if you want, you can use the product rule. If you want, you can expand it and differentiate it. Even if you were to expand it, you're still going to have to use the product rule because we're still going to have that t times e there. So let's just use the product rule straight away, I reckon. This is our function. T 0.1 t takes 6. All right, so for my u, I'm going to make that whole thing u. So the number, you don't have to include it, but you would have to multiply everything by it. You would have to have it out the front. So that's u. So then u dash is going to be minus 0.5. Dash. Alright, bit of text here to read. Let's make sure we get it right. During fermentation of a liquid, yeast in the liquid converts sugar into ethanol. The rate at which this conversion takes place varies during the fermentation depending on a range of factors. The ethanol produced by fermentation can be represented by A, where A is the percentage of ethanol in the liquid. In a particular fermentation process, the rate at which ethanol is being produced after T hours can be modelled by the function dA on dt. The graph is shown below. The graph has a y-intercept of 0.00744. Interpret this value in the context of the question. Y-intercept is 0.00744. So when time is 0, y equals 0.00744. What does that mean? What is on the y-axis for this function? This is the rate of change of yeast, the rate of change of yeast in the liquid, the rate of change of sugar into ethanol. All right, the rate of change of sugar into ethanol. A is the percentage of ethanol in the liquid. All right, A is the percentage of ethanol in the liquid. So when time is 0, the rate of change of sugar into ethanol is, all right, so that's the context of it. The rate of change of sugar into ethanol is, this is our value, 0.00744. What's the unit on the y-axis? Percent. A is a percentage, 0.00744% per period of time. What's our period of time? Hours. All right. And so the reason that's the case, so I might reiterate that one again. All right. It's a graph of, it's obviously a derivative function, dA on dt. So it's rate of change. What's the rate of change? Well, of sugar being converted into ethanol. This is the amount as a percentage, that's the unit, and that's our time period. So that's how we get that. Okay, after how many hours is the conversion of sugar into ethanol happening at the greatest rate? At the greatest rate. When's the greatest rate? So we can G-solve that max there. Yeah, I'll spend a bit of time doing that. Type out the function. G-solve the max, unless anyone's got it already. It looks close to 50, but it's probably just a bit above. Alright, make sure you get your V window the same as theirs, 0 to 60, and for Y, 0 to 0.2. G-solve that max. After how many hours? 50. Alright, so the graphs looks maybe my eyes are bad. T is 50. What is the percentage of ethanol in the liquid after 60 hours of the fermentation process? After 60 hours. Alright, so this function here, dA on dt, that tells you the rate at which the percentage changes. Okay? We want to know the quantity, we want to know the amount. Alright? We want to know the area under the curve from 0 to 60. Why? Because the area under the curve of a rate always tells you the quantity. So that's the integral we're going to perform. Integral from 0 to 60. I've got the graph, so I can do it straight off the graph. Integral from that function 0 to 60, please. Okay, so if the liquid ferments for 60 hours, our answer is 4.91%. Okay, so these marks, they're a little bit trickier to get, aren't they? They're sort of 1 mark, 2 mark questions, a little bit trickier. Alright, there's still another component to this question though. The fermentation stops after K hours when A equals 3.3%. Using your answer to part A, show that the integral of this equals this. Alright, so let's break that down. From part A, did I not bring those together or something?
No.
I just left it. Okay, I'll do that. I'm going to do that now over here. So we know if we differentiate this, we're going to obtain this derivative. So U dash V T U dash V. It's going to take 0.5 times 0.1. T takes 60. E to the 0.1, T takes 6. Okay, so we know if you differentiate this, you obtain this. Therefore, if you integrate this, you will obtain this. Okay, so that's the link we're making. All right, now they are interested in this component of it. So straight away, we're going to split the integral, right? So this is from exercise sort of 4E, where we're integrating by differentiation. So we want, that's why I pulled that off, we want this component of it, and so we're going to isolate that. And what I might do is I'm going to shove this component over here and move this one over here. All right, so I'm going to swap both of those. So when I swap them, because they're both negative, they're both going to become positive. So that's all I'm going to do in the next step. Alright, so that's what we're looking for. We've almost got it by itself. We just need to process that integral. So when you integrate e to the kx, it becomes 1 on top of k, e to the kx. So it's going to become 1 on top of 0.1. That's going to become 10. 10 times 0.5 is 5. There it is. Different. Why is it different?
They just get negative to start on the left.
Yeah.
That's a negative. Oh, we've got 35. So we've got, oh, let's expand it.
Yeah.
Let's expand it and collect like terms. Okay, so here we're going to have 0.5t e to the minus 0.1 t takes 6, and then we're going to take 30 e to the minus 0.1 t takes 6. I'm just going to leave that side for now rather than rewriting it, and then you've got these two alike terms, which collect to 35. Okay, so that's how we've shown it. Is that okay? All right. Fermentation stops after K hours when A is 3.3%. All right, 3.3%, so it has to be before 60 because we saw after 60 hours we had 4.9%. So we're going to find this value of K. What's this value of K for which it stops? Well, we know the integral from 0 to K of our function equals 3.3%. and we're going to find k. It says hence, so that means using what we just did. Using what we just did. So we've got the integral there. Even if we haven't been able to show it, we've got the integral statement there, so we'll just use that one. Alright, we're solving for k to 4 significant figures. So if we just break this down a little bit more. Alright, so I'm moving that over. That negative distributes, so we have there equals 0. And so then we're going to graph this function and g-solve the roots. We're saying, what's the value of k that makes this function equal to 0? So it can take a little bit of time to type it out and so forth, can't it? So let's see. Minus 0.5 x e to the 0.1 x take 6 plus 35 e to the 0.1 x take 6 take 38.3. G solving the roots. Might take a bit to graph. I expect it to be less than 60, right? We saw before between 0 and 60 hours we have 4.9%. So for 3.3% between 0 and 60, not found. Type something in there. Has anyone cracked it? Let's check. Minus 0.5 x e to the 0.1 x take 6 plus 35 e to the 0.1 x take 6 take 38.3 roots. Alright, so maybe we'll try equation solve.
I think that should be 0 and 35.
Oh, that one looks as a 0.
No, but the other one shouldn't be 35.
Oh, great figure. Yeah, look at that.
Okay.
Okay, good. Yeah, good.
Yeah,
Good, good. So look here. This is like a mistake I've made. You know, exam fatigue. When you put 0 in here, I've gone, oh yeah, that goes to 1. 35 times 1, that's how it goes. But that part goes to 0, but we do have this e to the minus 6 here, don't we? Yeah, good find. So then this component is not 38.3, it's 35 e to the minus 6 take 3.3. Alright, so then let's try now. 35 e to the minus 6 and then take 3.3. Nice one. $48.406. 4 significant figures. 48.41. Very good. Okay. All right. We've got a integral one involving cos x and cos 2x. All right. Show that an integral from 0 to pi on 3 of cos x plus cos 2x equals this. Okay, so we're just going to be processing that. Integral of cos x is sine of x, and integral of cos of ax is 1 on a sine of ax. From 0 to pi on 3. Sine of 0 is 0 here. We want to collect them together. They need to have the same denominator. The one we've got root 3 on 2 plus root 3 on 4. So we need to multiply this one by 2 on 2. And now 2 root 3 plus root 3 is 3 lots of root 3 on top of 4. Okay, so here, this was part of the old course. I've sort of edited it a bit so it's more appropriate for us. F of x is an even function if it is symmetric about the y-axis. Is f of x an even function? Can we classify it as that? All right. Is it symmetric about the y-axis? Okay, I'm going to sketch a graph up here, but you've also got the graph drawn on the book on the other page there. So you can see it's symmetric about the y-axis. All right, think about like the butterfly paintings you do back in kindergarten, where you paint one side, fold it in half, it's symmetric. Okay, use the information from parts A and B, find the exact value of the integral from minus pi on 3 to positive pi on 3. So if we consider the graph, I'm going to just sketch it roughly here. And we've done the integral from 0 to pi on 3. And we saw that that component was 3 root 3 on 4. Then if we want to know this whole thing, it has to be double, doesn't it? So it's going to be 6 root 3 on 4. What's that simplified to? 3 root 3 on 2. Okay? Give reason for your answer, okay? Because f of x is an even function, the integral from minus pi on 3 to 0 is equal to the integral from 0 to pi on 3. So something like that would be appropriate. The graph is shown below. Find the exact value of k such that this function has a minimum value. Find the exact value of k such that the function has a minimum value. Alright, the integral. So we're saying k lies somewhere in here. K is somewhere between minus pi and positive pi. Find the exact value of k such that the integral from minus pi to k of the function is minimized. So we want the smallest area. So the first thing we're going to do is let's say, well, what on earth is this area here? Because that's going to help us make a decision about it. What is the area from minus pi to minus pi on 3? And we know that that area is going to be the same as positive pi on 3 to positive pi. So let's check that, what that area is. Cos x plus cos 2x. Get your b window the same. Minus 2 pi pi. And then 1.299, okay, which is the exact same as this, I reckon, and you can check it. We go 3 root 3 on 4. So decimal 1.299. So that's fascinating. These have the same area. They have the same area. So if we want this area to be minimized, if we want the area to be minimized, well, K has to be at 0, all right? And the reason it has to be at 0 is because this area, the area of that segment, segment A, plus the area of segment B, it's stopping at the Y. The area of segment A plus segment B equals 0.
Connor Harrison,
And so that's when it's going to be minimized. We can't get
Connor
any
Harrison
less
to the
than
front
0.
office, please.
Alright, so K equals 0. So that's quite tricky to get 1 mark there. There's a bit of thinking involved. Alright, let's move on. Is this the last one? Yep. Okay, nice, last one. And it's a kinematics one. And so I did make this a bit longer because I did want to put these sort of last 3 questions in there. So yeah, we're going an hour and a half now. So we'll finish up this last one here. Alright. We got, consider the function, show that f dash of x is this. Alright, so there's a bit going on there. We've got f of x is a multiplied by x plus 20 on the 7, ln of 1 plus 9e to the minus 7 on 20x. Take 1 on 10x. Alright, now there are like terms in there and things we can collect and so forth. We're not going to do that, we're just going to differentiate straight away. So for f dash of x, okay, a is going to stay out the front, and we can see that in what it wants us to show. So show that derivatives, we've still got a out the front. X goes to 1. Alright, 20 on 7, that's going to stay there. And we've got ln of a function. Okay, ln of f of x, and so then the derivative is going to be f dash of x. That is 9 minus 7 on 20 e to the minus 7 on 20x. Okay, that's the derivative of this component. So ln on this and the 1 on 10x goes to 1 on 10. Alright, so a little bit tricky. F dash of x on top of f of x, that's the same. The denominator is the same. That one we've differentiated. We've just pulled the k value out the front. Okay, now we've got to simplify it a bit though, don't we? So, look carefully. We've got this 1 on 10 hanging out the side there. So we're not going to change that. We've got the a, so we're not going to change that. We do have this 1, and we are going to bring that together a bit. And it also can be simplified. Look here, we've got this number multiplied by this fraction. And here we've got 20 on 7, and here we've got 7 on 20. So they can actually cancel. Alright, when you multiply a number by a fraction, remember it goes to the top. So that can cancel. And so we're left with minus 9e here. And if we want to, maybe I'll restate it so I can show it very clearly. Okay, if we want to bring those together, because the 1 isn't in the answer we're looking for, they've got rid of that. We want to collect them, we need them to have the same denominator. So we're going to replace this with this. Alright, that's still equal to 1. Okay, and now they have the same denominator, we can bring them together. Show it very slowly because it's quite complex, the terms that are going on. That one's negative. Alright, 9e to the minus 7 on 20, take 9e, they cancel it. And that's how we're left with the 1 at the top. Alright, so we've shown that. Okay, here we go. Sergi and Thomas run on a circular running track. They start together and run around the track for 20 minutes. Sergi's running speed after 10 minutes of running can be modelled by this function. On the axis, sketch a graph. Okay, so we've got a wire, we've got a V window. Let's sketch that one up. We're going to go here for you guys. We've got 0.09 e to the power of minus 0.11 x. So our V window the same. Here we go from 0 to 20. And 0 to 4. Oh, I'm missing an x. 0.09 x e to the minus 0.09. Alright, so that's good. That's what the graph looks like. Alright, what is the total distance that he travels? Okay, so distance is going to be area under the velocity function. He's not changing direction, he's only running in the same direction, so we don't need to consider other directions. There's probably a way to do it on Desmos. I won't look it up now, I'll just mash it in here quickly. So 0.09 x e to the so that's area under the curve from 0 to 20. So I'm doing, what am I doing, guys? Integral from 0 to 20 of v of t, v of Sergi, integral 0 to 20. .8. Now we need a unit. All right. The speed is in kilometres per hour, so the distance is going to be in kilometres. Pretty quick. Thomas's running speed after t minutes can be modelled by this function. That's the function that we had before, isn't it? On the axes above, sketch both functions together. Okay. Determine the point of intersection. So I'm going to sketch it on my calculator rather than on Desmos. That's not particularly helpful for us. We have 0.3 out the front. We have 1 on top of. Minus 7 on 20x. Take 1 on 10. Close the bracket. Evaluate. This is 0.3. Alright, G solve that intersection. And we've got, so yeah, you get a mark. Careful here because it says sketch the graph. Some people will miss that kind of thing and they'll jump straight to the next one. So make sure you look out for that. Determine the point of intersection. We've got 15.17 and 0.257. 15.17 and 0.257. Okay. Determine the point of intersection on the graph you have sketched. Points. Alright, well there is one at 0, 0. They both start at the same time. What is the significance of the points of intersection in this context? Both start at the same velocity. Remember, this is a graph of velocity. After 15.17 minutes, the second guy is running the same velocity as the first guy. So, after Thomas is is running the same. Right, because after that, after 15.17, Thomas is running faster, but before that, Sergi is running faster, right? Okay. What is the total distance travelled by Thomas in his run? So that's going to be the integral from 0 to 20, the velocity of Thomas. So let's determine that. So they're both running for the same amount of time. And then we've got one more part, almost done. G self integral 0 to 20. .43. So he was running slower, and for that reason, in 20 minutes, he's run a fair bit shorter. All right. Consider the function. When used as a model for Thomas's running speed, the value of A is related to his maximum speed. Thomas believes he can increase his maximum speed if he undertakes more training. Using part A, determine the value of A in this model for which Thomas runs 5 kilometres in 20 minutes. So for Thomas to run 5 kilometres in 20 minutes, it means the area under his velocity function, which is this one. Integral from 0 to 10, that's his velocity function with regards to t, equals 5. Okay, for him to run 5 kilometres, the area under his velocity function has to be 5. We're solving for A, right? So we can pull A up front. And 1 plus 9 e to the minus 7 on 20. There's a t there, take 1 on 10. Alright, now we know what this component integrates to. Of course, if you're using technology and you want A by itself, you can just divide that over there. You can go 5 divided by it and you're going to get the value A. It does say using what we have, using part A. So I'm going to flip back to there. And I know that it integrates to this. We're going to have A times, we've got X plus 20 on 7 ln of 1 plus 9. It's a mess. Take 1 on 10 X. Alright, sub 20 in, sub 0 in, and then 5 divided by it. I'm just going to put this part in my calculator. It doesn't say to do it exactly. I think we've shown it up there. Does it say to do it exactly? No. So 5 on top of the integral from 0 to 20 of Thomas's velocity function. Let's evaluate that. Alright, so if I was writing it all out properly, I would like this, showing the fundamental theorem of calculus, simplifying it a bit, collecting it, and then shoving it over. I'll leave that for you guys to have a go at if you're interested. So instead, 5 on top of, what we got? 1 on top of. Minus 7 on 20 x 0.437. There we go. Alright, so a little bit longer. But it's about 10-15 marks longer. I can't remember exactly. So yeah, all of that, all stuff that's relevant. So yeah, thanks for coming along. You're welcome to stay. Thank you. You can hit the stop.